Go.
Good day, everyone. Now we are going to solve problem number 2 in chapter 4 from the book Process Systems Analysis and Control by LeBlanc. To start with, a mercury thermometer bulb is 1/2 inch long by 1/8 inch diameter. The glass envelope is very thin. Calculate the time constant in water flowing at 10 feet per second at a temperature of 100 degrees Fahrenheit. In your solution, give a summary that includes assumptions used, sources of data, and the results. Our problem is to calculate the response or the time variation of the thermometer reading for a particular change in the fluid temperature at 100 degrees Fahrenheit. In this analysis, the following assumptions will be used. First, all resistance to heat transfer resides in the film surrounding the bulb. That is, all resistance to heat flow is in the outside film. Next assumption is that all heat capacity is in mercury. Furthermore, at any instant, the mercury assumes a uniform temperature throughout. To solve for the time constant, the following data will be used. For the water at 100 degrees Fahrenheit, the Cp will be 1 BTU per Lb degrees Fahrenheit, the K will be 0.36 BTU per feet or degrees Fahrenheit, and the viscosity is 0.72 centipoise, which we will convert into Lb per feet R. So we will multiply this with 2.42. This will be equivalent to 1.7424 Lb per feet R. For the mercury at 100 degrees Fahrenheit, the Cp will be 0.033 BTU per Lb degrees Fahrenheit, and the specific gravity will be 13.6. All these data are from the book Process Heat Transfer by Kern. Also, the following equations will be used. The Nusselt number, which is equal to Hd over K, is equal to B times Re raised to N times 1.1 times P times the Prandtl number raised to 1/3, which is from the book Bennett and Myers, 3rd edition, page 391, equation 24.9. From the Reynolds number and the Prandtl's number, the correction factor B and N will be 0.174 and 0.618 respectively. So this formula will be Hd over K is equal to 0.174 times Re raised to 0.618 times 1.1 times Prandtl's number raised to 1/3, where the Reynolds number will be solved from dV rho over viscosity, and the Prandtl's number will be Cp times viscosity over K. For the time constant, the equation that will be used will be tau is equal to mc times over Ha, where m is equal to mass of mercury in the unit of Lb, and the c is the heat capacity of mercury with the unit BTU over Lb times degrees Fahrenheit, and the h is the film coefficient of heat transfer, which in the unit BTU over feet squared times height times degrees Fahrenheit, and the a will be the surface area of the bulb for heat transfer in the unit feet squared. This formula is from the book Process Systems Analysis and Control found in page 74. The next step will be finding the film coefficient of heat transfer H using this formula. Hd over K is equal to 0.174 Re raised to 0.618 times 1.1 times Prandtl's number raised to 1/3. First, we will solve for the Reynolds number. So Reynolds number is equal to dV rho over mu. The diameter is 1/8 inch, and we will convert this to feet, so we will multiply it to 1/12 feet. Next is the velocity, which is 10 feet per second, which we will convert this into hours, so we will multiply 3,600 seconds over 1 hour, times the density of the water, which is 62.5 Lb per feet cube, over the viscosity of the water, which is 1.7424 Lb per feet R. We will now multiply these values and we will get a result of 13,451. For the Prandtl's number, which has the formula Cp times viscosity over K. The Cp of the water is 1 BTU over LB degrees Fahrenheit, and the viscosity is 1.7424 lb per feet r. And the K will be 0.36 BTU per feet r degrees Fahrenheit. Multiplying these values, we will get a result of 4.84. So now, substituting this Reynolds number and Prandt's number in the correlation, we will now have HD over K is equal to 0.174 times the Reynolds number we have computed, which is 13,451, raised to 0.618 times 1.1, and the Prandt's number, which is 4.84, raised to 1/3. Multiplying that, we will have HD over K is equal to 115.2906. To solve for H, so we will divide this with, it will be 115.2906 times K over D, in which the value for K is 0.36 BTU per feet r degrees Fahrenheit over the diameter, which is 1/8 inch, and converting this into feet, we will have 1/12. We multiply this by 1/12 feet. So the H will be 3,984.44 BTU per r times feet squared times degree Fahrenheit. To solve for time constant, we must first find the surface area of the bulb and also the mass of the mercury. So the area will be A is equal to pi dl and pi over 4d squared. The pi dl will be for the cylinder part of the bulb, and the pi over 4d squared is for the circle part. So now we will compute pi times the diameter is 1/8 inch and the length is 1/2 inch plus pi over 4 the diameter times d squared, which is 1/8 squared. So the area will be 0.2086 inch squared. Converting this into feet squared, we will now have 0.00145 feet squared. Now, in order for us to solve for the mass of mercury, volume must first be computed. So the volume for the mercury will be computed from the formula pi over 4 times d squared times the length. So this will now be, substituting the values, this will now be pi over 4 times 1/8 squared times 1/2. This will be now equal to 0.0059 inch cube. Now we will now solve for the mass of mercury, which is equal to rho V, density, and density times volume. The density of the mercury is equal to the specific gravity of the mercury times the density of water times the volume. So specific gravity of mercury is 13.6 times 62.4, the density of water, and the volume of the mercury, which is 0.0059 inch cube, and converting this into feet cube, we will now have 0.0029 pounds of mercury. Now, we finally compute the we can finally calculate the time constant using this formula. Tau is equal to mc over HA. This will be now equal, substituting all the values we have computed, which is the mass which is equal to 0.0029 lb times pounds times the heat capacity, which is 0.033 BTU over lb degrees Fahrenheit. This is the heat capacity of the mercury, over H, which is 3989.44 BTU per R per feet squared times degrees Fahrenheit, and the area, which is 0.00145 feet squared. Multiplying all these values, we will now have an answer of 1.654 times 10 raised to negative R, and we will convert this into seconds. We will multiply a conversion factor of 3,600 seconds over 1 hour. So now we will finally arrive at the answer, which is tau is equal to 0.059 seconds. This is the time constant for time constant of the problem. Tau is equal to 0.059 seconds. Thank you for listening. I hope you found this useful.